So before we get to probabilistic inference, we need to introduce a couple of important rules. Sometimes we have conditional distributions, but we want the joint distribution. So the product rule allows us to get the joint distribution if we have the conditional distribution. So the product rule can be easily derived from the definition of conditional probability. Remember, we said by definition, P of x given y is equal to P of x y, the joint distribution, divided by P of y. So multiplying both sides by P of y, we get P of y times P of x given y is equal to P of xy. So this here is the product rule. It allows us to compute the joint distribution if we have the conditional distribution and the prior. P of y here is called the prior. A more general form of the product rule is the chain rule. It's also called the general product rule. It allows us to write any joint distribution with an arbitrary number of random variables as a product of conditional distributions. So if we have three variables, x1, x2, x3, we can write that the joint distribution of x1, x2, x3 is equal to p of x1 times p of x2 given x1 times p of x3 given x1 and x2, and so on. And the more general form is given for n variables. So the joint distribution with n variables is equal to the product of the conditional distributions for I equals 1 to n. So there are two ways to factor a joint distribution over two variables. We can write P of xy equals P of x given y times P of y. That is the product rule, right? It follows from the definition of the conditional distribution P of x given y. But we can also write that P of xy is equal to P of y given x times P of x. And this one follows from the definition of the conditional distribution P of y given x. So now we have this equality here, P of x given y times P of y equals to P of y given x times P of x. We can divide both sides by P of y, and we get P of x given y is equal to P of y given x divided by P of y times P of x. And this is Bayes' rule. This is one of the most important rules in AI. Why is it helpful? Because it allows us to build one conditional from its reverse. So what happens is that very often one conditional is tricky to compute while the other one is simple. This rule allows us to compute this tricky conditional. It's the foundation of many systems in AI, in speech recognition, in machine translation, and in many more. And it's really one of the most important equations in AI. So what is probabilistic inference? It is the task of computing some desired probability from other known probabilities. We generally compute conditional probabilities. These probabilities represent the agent's beliefs given the evidence we have so far. Probabilities change when new evidence is received, and observing new evidence causes beliefs to be updated. So this is Bayes' rule written in terms of cause and effect as opposed to x and y or a and b. So probability of a cause given an effect is equal to the probability of the effect given the cause times the probability of the cause divided by the probability of the effect. So the effect is what we observe. The effect is usually our observed variable, and the cause is unknown. It's our unobserved variable. We would like to determine its probability. So for example, a robot needs to infer its location from some noisy sensor reading. The cause here is the location of the robot. The effect is the sensor reading. It's easy to measure the distribution of the sensor given the location, we can simply place the robot at different locations and take measurements. We can then compute the distribution of a location based on a given sensor reading with the help of Bayes' rule. So let's look at another example where we use Bayes' rule for diagnostic probability. Let's say the random variable m represents the fact that a patient has meningitis. Random variable s represents the fact that the patient has a stiff neck. We are given the marginal distribution for the cause, p of plus m, meningitis. We are also given the conditional distribution for s, given plus m and minus m. These are relatively easy to measure. Out of all the patients who have meningitis, we count how many have a stiff neck. And out of patients who do not have meningitis, we count how many have a stiff neck. And we compute these probabilities. So a patient comes to us with a stiff neck. We need to figure out what is the probability that they have meningitis. So the quantity we are interested in here is P of plus m given plus s. The probability that they have meningitis given that they have a stiff neck. So how do we compute that? We apply Bayes' rule. So the cause here is m and the effect is s. So P effect given cause is P of plus s given plus m times P of plus m divided by P of plus s. So P of plus s given plus m is given to us here, it's 0.8. And P of plus m is also given to us, it's 0.0001. But what is P of plus s? So P of plus s is the marginal distribution of s. If we had the joint distribution table here, we would be selecting the rows corresponding to plus s plus m and plus s minus m and summing them up. So we can still write that P of plus s is equal to P of plus s plus m plus P of plus s minus m. This is the marginal probability of s. So what is P of plus s plus m? We don't have that joint probability, but we have the product rule. And by the product rule, we know that P of plus s plus m is equal to P of plus m times P of plus s given plus m. And similarly, P of plus s minus m is equal to P of minus m times P of plus s given minus m. So we can replace P of plus s plus m by this product, and we can replace P of plus s minus m by this product, and we get that P of plus s is equal to P of plus m times P of plus s given plus m plus P of minus m times P of plus s given minus m. So here again, P of plus m is given to us. This is P of plus m. P of plus s given plus m is given to us. P of plus s given minus m is given to us. But what is P of minus m? It's not given to us. Can we compute it easily? And the answer is yes. P of plus m and P of minus m have to add up to 1. So P of minus m is equal to 1 minus 0.001. So we can plug in our numbers and we find out that the probability that the patient with a stiff neck has meningitis is 0.008. So let's go back to homework 8 and see how we can use Bayes' rule there to help our agent find the treasure. So we'll use t as our random variable here. In the example here, we are considering a small grid, a 5 by 5 grid. So the domain of t is any of these locations. So there are 25 possible values for t. Initially, the distribution is uniform because before we have made any measurement, it's equally probable that the treasure is in any of these locations. Since we have 25 possible locations, the probability of the treasure being in any of these locations is 1 over 25. So we are also given our sonar model. That gives us the probability of a sonar reading given a treasure location. So we know what our sensors do. And then we go into sonar mode and we read at this location, at 1, 3, let's say. We get a green reading. Our sensor model gives us the probability that the sensor reading is green given t is at any of these locations. So we have p of s equals green given t, for t being all of these sensor locations. So what we need to compute the posterior distribution. We need to compute the distribution of t given that green sensor reading over the treasure locations using Bayes' rule. So for each of these locations, we're going to compute the probability of the treasure being there, given that we have a green reading at this location here. So we apply Bayes' rule. We write that P of t given S, probability of treasure being at each one of these locations, given a green reading at this location here, is equal to the prior, to the marginal probability P of t times P of S given t. P of S given t is given to us by the sensor model, divided by P of S. So we have to compute this quantity for the 25 possible locations, the 25 values in the domain of t. And this P of S here is the same for the 25 values. So we will say that this quantity here, P of t given S, is proportional to P of t times P of S given t. This sign here, alpha, means proportional. So what we'll do is we compute this product, P of t times P of S given t, for all possible treasure locations, and then we'll normalize. So the probabilities will have to add up to 1. We have a single treasure here, and it has to be in one location. So all these probabilities must add up to 1. So if we compute the sum of this product here for all the treasure locations, and then we divide by the sum, we divide this product by the sum, we get the posterior probability that we wanted. Okay, and that's the probability of the treasure after the reading, given the green reading. And now we're ready for the next reading. At this point, the prior distribution is no longer uniform. So now we have to work with this distribution here. That becomes our prior. We take another reading. So let's say we read a yellow at this position here at 4, 0. Our model can tell us what's the probability of a yellow given t for all these treasure locations. We calculate the posterior distribution now by using Bayes' rule. So again, here we know that P of t given S is proportional to P of t times P of S given t, except that P of t here is no longer the uniform distribution. It's the distribution we had before this last reading. And we keep doing that after each reading. So after each reading, we update our beliefs and we generate a new distribution. And this represents our beliefs at this time, given the sonar readings we have so far.